Hello everyone, welcome to Unit 3, Crystals, Section 3, Crystal Defects. Now usually when we think defect, we think not good, right? Bad part of it. But actually what we're going to be doing in this unit, we're going to talk about how defects can affect crystals both negatively and positively, because we actually use them quite often in material science, the defects that are there. So instead of thinking of them as bad things, okay, I want you to think of them as imperfections, not bad, okay, or another word, imperfections, or let's call them impurities. So right there, what are crystal defects? They're impurities or disruptions in the pattern of the atoms. Remember that crystals are repeating units, ordered structure, so that pattern is being disrupted in some way. Okay, because this is happening, again, we're talking about physical properties, back to those slip planes, back to that workability, because it's affecting how they're ordered, that structure of them, it does affect their physical properties. There are three main types of crystal defects: point defects, line defects, and interfacial defects. So we're going to start off with point defects. I think these are the easiest because they make the most sense. The names are pretty easy. When we talk about point defects, we're talking about one atom in the crystal being affected. So single atom defects. There are three main types, and it's pretty easy. Vacancy, well, what do you think that might be? Well, a vacancy in the crystal is the atom is missing. It's vacant. It's gone. Okay, so where we have vacancy, so there's a void in the crystal structure, nothing there, it sort of stops movement. Basically what's happening is the atoms are moving around and somebody moved out of place and nobody's filled it up yet. Now, as far as examples go, there aren't any specific examples because this can happen with any of them. But go ahead and draw a little quick picture of what is on here. So you have your ordered structure, circles, your atoms all lined up, and then you have these two spots missing there. Okay, I don't have any specific examples, but that is your example. It can happen in any crystal. Okay, so that's vacancy. The next one is interstitial. Now this one's a little harder to talk about, but inter means between, like interpersonal, between two people, interstate, between two states, right? So interstitial means between two atoms. In other words, it's extra atoms inserted the gaps between the regular atoms. Okay. This most common example, most example you're most familiar with, would be steel. Okay. We use interstitials a lot for making alloys. These atoms in steel would represent the iron, and then the smaller atoms that have gone between them would be the carbon. And this is how you make steel, and this is actually how you make it stronger. So again, it's a defect, but it's something we like. We want to have strong steel. Now, can we have can we have too much carbon in there? Yeah, it can actually become brittle and cause it to break. But we do like it, but it gives that steel strength. So there's that perfect imperfection, how it works. Okay. The last type of point defect, again, single atom defect, is substitutional. And like a substitute, it replaces something. So you're replacing, it's not disappearing. You're replacing the original atoms with different atoms. Okay. Again, this is another way that we use to make alloys. Okay. Examples of substitutional would be bronze, when copper is replaced by So I got mixed up with brass, because brass is another one. Whoops, wrong one. Brass would be copper being replaced by tin. Bronze is your other alloy there, so those atoms are being replaced by other atoms. So those are your 3 point defects: vacancy, something missing; interstitial, something going between, and substitutional, something being replaced. Okay. The second type of defect, we have line defects. We actually call these dislocations because of what they do to our lines. Instead of affecting one atom, you're affecting a whole line of atom. And I'm actually, let me go ahead and go up here. So this is an example of an interstitial. You can see this extra piece here. It's not just one atom being affected, but these whole lines, this, so you can see it. This whole area, these two lines, are being affected by this line right here. You can see how it's actually sort of like an extra line. And that's what we have with dislocations, okay? Those crystals are no longer perfectly aligned because they have that extra plane in there. So there you go, have that extra plane being pushed in front of it. Okay? Now the really cool thing is they can move. Okay? If you take a look at this little, not it's an animation, little picture. Here's your defect. Okay, those are the extra plane. But we can move and we can manipulate those atoms because of the slip planes. We can move them along, go from the middle, up one more, add more force, and push it off. And we like these things. Okay? Why? Why do we like these things? Well, because if we have a small number of them, it makes them more workable. Again, those slip planes coming back. More slip planes is good. So having those those line defects, those dislocations, can actually push those slip planes along. So it makes it more workable. However, if we have too many of them, it actually makes it harder for them to work. Okay? Why? Well, it's like too many cars on the road. Some cars are good, but too many, they all get jammed or pinned together. They just can't move anymore. So dislocations, we like to have few, but not too many. So they can be more workable. Okay. I do have one more picture there for you. Here's this guy. It's a little easier to see. It's hard, you can't tell, but here's an extra line right here, another line over there, and this actually allows all that movement in metal atoms. I like this one because you can't really, it's hard to see it right away like these other guys, but you can tell that there's something wrong. Okay. Alright, last type of defect is what we call an interfacial defect, and it actually sort of like it sounds, interface, face being the cover, what you see. This has to do with grains. A grain is a crystal that starts growing from different place and meets up. In other words, guys, when we have crystals will join together to make one big solid, but the crystal itself, that one repeating unit, will meet up. That's a grain size. Okay, you usually have multiple crystals in one atom. Okay, from my bismuth crystal, that's the one that sits on my desk is multiple crystals in one. Okay. Now where they meet up, these lines, and here you can see crystals here, the repeating units. The lines where they made up, they're called grain boundaries. Okay, so definition of grain boundary, where grains meet up in a solid. Okay, that is that face there. That gives you the interfacial defect. Okay, these are these interfacial defects. They again occur at grain boundaries. Okay. They are, and that one should be underlined, guys, just so you know. Okay. All right. There you go. These are 3D defects. In other words, they have multiple planes that they affect at one time, not just one direction. Okay. And then the number of and size of grains can affect those physical properties. Small crystals, of course, since they're small, they're going to have more grain boundaries because more fit in that area. And more grain boundaries actually can make a metal stronger. And that's part of those interfacial defects, those jams coming together, that movement stopping. So we like having, again, a defect helps make our metal stronger. So smaller crystals make them stronger because they have more grain boundaries. Okay, it has to do with those dislocations moving anymore, and that stopping any slip planes from working. Okay, the quick cooling process, and we learned this from section 1, quick cooling process creates small grains and therefore stronger metals. And so we're going to be working with these interfacial defects and dislocations when we talk about working metals. And you can see here, I just want to really quickly go down to this picture. This is a 3D display of grain boundaries, okay? And this line right here where those two grains meet, this is your interfacial defect. Okay? And any movement that happens on this guy is going to be stopped at that grain boundary and not be able to move on that guy. So we have a stronger metal. Right? Right. Last, and it's on, I put it in defects because it can actually be a big problem. Okay. Not that it's a defect, it's actually a type of growth. We have dendrites. They are crystal branches that grow in multiple directions. One example that you have seen is a copper and silver nitrate. Under the microscope, you should have seen that. You're also going to make observations with the tin sponge. You're going to making a picture. You're going to be watching these dendrites grow, and you're going to be reading about how dendrites can cause a problem in turbines, so that they make. And that's with the section 1 reading as well. Now, crystal defects, again, they're not bad all the time. We can actually use them, and we do use them in computer chips as well. So you should be doing your reading perfectly imperfect computer chips and see what happens. All right, so have a great afternoon, and we'll catch you later.